This is episode 1 of the RC Test Flight Propeller Design Competition. About 6 weeks ago, I made a video detailing the rules of the competition and how I went about setting up this drone boat to automatically measure the efficiency of whatever propeller is attached to it. Since then, there have been over 50 submissions, and I chose to print 24 of them. As of now, I've already tested all 24, but 24 is a lot of propellers for a single video, so I'm going to split this up into 3 videos. We'll take a look at 8 propellers per video. At the end of the third video, the overall winners will be announced. The prizes are store credit to PCBWay. The first place winner gets $300, the second place gets $200, and the third place $100. So in this video, I'm going to be testing these propellers. Let's meet our first 8 contestants. The very first submission I got to this competition was from someone who literally just downloaded the baseline propeller and resubmitted it without making any changes. And they said, use a super hydrophobic coating on it. Now, I've actually gotten a lot of comments in the past from people telling me I should try super hydrophobic coatings on propellers and boat hulls. So I figured this competition is the perfect opportunity to try it out. I'll test the baseline propeller before and after the super hydrophobic coating is applied to see if it does anything. For those of you who didn't watch the intro video, the baseline propeller is designed to be like an average kind of middle of the road boat propeller that we can use to compare all the other propellers against. I arrived at this design by testing out a ton of different diameter and pitch angle variations, and this is what happened to work best with our given motor. So the first actual submission is the twin turn-up, and it was submitted by Josh Fisk. He says the idea here is to reduce drag by going down to 2 blades instead of 3. And he also made a streamlined tip at the end of the hub to hopefully get rid of that stagnation area that we were seeing in both the Air Shaper simulation and the underwater GoPro footage from the baseline propellers. I asked each contestant what their confidence level was that they would win, and Josh's was a 5 out of 10. My thought is that it's pretty likely that this propeller will outperform the baseline. It's pretty widely accepted that 2 blades are more efficient than 3 because you can make each blade longer. I think most boats just use 3-bladed propellers because it reduces the gyroscopic precession wobble that you get with 2 blades. And also they're trying to get more thrust, more peak thrust out of a smaller diameter because, you don't want your props hanging down too low and then sticking up out of the water. So that's why I think that's why 3 blades are more common. Our next contestant is the Spin Doctor, and this was submitted by Jacob. He says that he actually uses this propeller on his e-foil board, and it's roughly comparable to a B-series propeller. For those of you who don't know, the Wagening B-series propeller, Wageningen? I don't know how to say it. Wageningen B-series design is probably the most popular boat propeller design on the planet. It's, that one that looks like this. You've probably seen it on a lot of big ships and boats of all types. Jacob's confidence level is 6 out of 10, and this propeller just so happens to look really similar to the toroidal propeller that Heinrich from Friendship Systems made for me, and that was shown in the first video. That propeller did outperform the baseline propeller, and this propeller looks almost identical, so I'm guessing this propeller will also outperform the baseline. Next up is the Ring Glide propeller, and it was submitted by Frank Sprowitt. He wants to reduce drag by eliminating the tip vortices and ensuring gradual flow of water into the propeller. His confidence level is only 4 out of 10 though. For some of these bigger, crazier props, I'm just going to FDM print them because it would take a ton of resin, and I'll be honest, I'm not super confident that this will work really well. The main reason I'm not super confident is because these blades are like Batman shaped. I don't even know how to describe that, but the tip cord is like 180 degrees, so this is just going to have way too much rotational resistance to actually work well. I'm printing the FDM printed props on the Prusa XL, and I'm using PETG for the actual propeller itself and PLA for the support material. And PLA does not stick to PETG, so that makes removing the support material super easy, which is nice. Another thought I had is that there's a ton of surface area out on the outer diameter of the propeller, and that's where things are moving the fastest, through the water. So there's gonna be a ton of parasitic drag on this. Next up we have bigger parentheses, diameter is better. This was submitted by Nerd1000. He said that instead of studying for his PhD thesis defense, he designed this prop using a tool called JavaProp. Basically, his goal was to maximize the span given the allowed print volume and utilize high aspect ratio blades. And his confidence level is 6 out of 10. What's with all these low confidence levels, people? Come on, have some faith in your design. So sailplanes use super long, narrow blades because they're really efficient. They have a good lift to drag ratio. So the question here is, will that concept apply to propellers? I think it probably will if they don't snap. All these propellers are printed on the Formlabs Form 3 Plus with Gray Pro resin, and this stuff is really strong. It's really good for a resin printer, but you know, that's a pretty thin blade, and we're going to be putting 400 watts of power into it. So if it doesn't break, I bet this propeller will be really efficient, but we'll see. Resin printing is also really good for propellers because you don't get all the little layer lines that you get with an FDM printer. So it's got a nice smooth surface finish, and that should reduce parasitic drag and hopefully be pretty efficient. Next up, we have nodules and feathers, and this was submitted by James D., who is a product design engineer. This propeller is basically identical to the baseline propeller, but it has the leading edge of a whale's fin and the trailing edge of a bird's wing. He thinks these nature-inspired features will add vortices, which will reduce flow separation and hopefully increase efficiency. His confidence level is 7 out of 10. A few months ago, I had a ton of people send me a video about bionic propellers, and apparently adding tubercles like those on a whale's fin can delay the onset of flow separation and help the blade continue operating at a higher angle of attack. And apparently it also makes the blades a lot quieter. And at the end of this video series, so in the third video, I'm going to be using an underwater microphone to measure the noise levels of a few of these propellers. So don't forget to subscribe so you don't miss all of the videos. My hunch for this propeller is that it's probably not going to be any more efficient than the baseline, but I don't doubt that it could be quieter though. That'll be interesting. The Paunovic propeller was submitted by Nenad Paunovic, and he says this is a patent-pending propeller that uses a new complex blade design, and it's proven to be quieter and more efficient than a regular drone propeller. But I emailed him because his original submission had trailing edges that were too thin to print, and in that email I also said, hey, this is just a hunch, but I'm pretty sure the angle of attack is way too low for this thing to perform well. And he replied saying that he's quite confident in his CFD simulations, so his confidence level is 9 out of 10. My hunch is that there's just no way this thing is going to perform well, and that's only because of the angle of attack. The blade design, I have no idea. It might be great at a higher angle of attack, but the angle of attack is just going to kill it. Also, I think it might break. Like, this thing is super flimsy. He said this design is made for metal and we're making it out of plastic, so here's a fun one. The Fibonacci flippers was submitted by Will. He says that this design supposedly makes for really good wind turbines, so why not reverse it and throw it in the water? He hopes that maybe reversing the direction might create a large amount of thrust with a semi-decent efficiency, and his confidence level is 7 out of 10. I don't think it's going to come anywhere near the performance of the baseline propeller, but if it pushes the boat, that'll be pretty cool, so I'm excited to see this one. Last but not least, we have the Mars Glider, and this was submitted by Joker1. He says that since these propellers are operating at lower Reynolds numbers, he's using a low Reynolds number airfoil, and this specific airfoil was developed for the Japanese Mars Glider. I googled around for a Japanese Mars glider and I couldn't find anything, so I really don't know what he's talking about. But right after he submitted this design, the company Micronics 3D reached out and offered to print a propeller. So I said, sure, you can print this one. And they did. Micronics is developing a SLS printer that doesn't cost $1 bajillion. So that would bring SLS technology to the high-end hobbyist market, which would be pretty awesome. This prop feels pretty strong. It's made out of nylon and it's also lighter than I thought it would be. The surface finish is rougher than the SLA printed props, but I can probably smooth that out later somehow. So those are all our contestants for this first video. But this is going to be a pretty boring competition if we can't actually see the propellers doing their thing. So I need to devise some sort of a underwater high-speed camera setup to take video of these propellers spinning. The first thing I tried was attaching this FreeFly Ember slow motion camera onto the boat, along with a probe lens that will stick through the surface of the water. The cylindrical shape of the probe lens is going to have a ton of drag, and that'll make it really difficult for the boat to go fast. So I 3D printed an airfoil shaped sleeve that fits over the end of the probe. One of the downsides to probe lenses is that they do not let in very much light. This one is f14 for all you camera people out there who know what that means. Plus, high-speed cameras have super fast shutter speeds and also need a ton of light. So even direct sunlight is not going to be enough for us. But luckily, I happen to know a guy who makes these awesome high-powered LED modules that can be powered with LiPo batteries. They are typically used on drones to light up things from the sky, but they should also be perfect for this application. The reason I'm trying to build this camera setup onto the boat is so that we can actually see what's happening with the propeller at speed. It would be much easier to film while the boat is just tied up at the dock, but then we'd only be seeing what happens during static thrust, which is far from the optimal condition for these propellers. They're optimized for speeds between 2 and 3.8-ish meters per second, or at least they should be if they're going to have any chance at winning. When I'm testing propellers at the lake, I need a way to keep my computer and camera batteries charged, and for that I'm using the Opus Exodus 600. It's a portable power station that has 256 watt-hours of battery capacity. That's enough energy to push this boat for 22 miles at a speed of 2 meters per second. It features dual 600-watt AC outlets, USB A and C ports, a 12-volt DC output, and inputs to connect solar panels. It can charge it up to 240 watts from solar alone, and when charging it with AC, it can fast charge in just over 30 minutes. When I say I use this thing a lot, I'm not kidding. I've just started keeping it in my car because it seems like I need it every time I leave home. I've used it to power all my devices during countless autonomous boat missions, and when I need more power to charge big drone batteries, I bring the Opus Mega 5 that can do up to 4,000 watts. But the Exodus 600 is even powerful enough to run smaller power tools, which is great for fixing Colin's car. Opus is running a program called Opus Help, where 5% of their sales go towards providing power banks for those in need. This helps keep the lights on for hundreds of recipients who live in places with unreliable power or who struggle to pay the power bill. If you're interested in the Opus Exodus 600, it's available now on Amazon or from opus.com. Check the link in the description for more. Now back to the video. So here's what the video looks like. The first thing I realized is that 600 frames per second is borderline too slow for looking at these propellers. They're spinning at around 1700 RPM, which is 28 revolutions per second. That means the camera is only capturing 20 frames per rotation. It's not terrible, but it's maybe not the best way to see what's going on with the flow. Here I put some food coloring in the water. It looks pretty cool, but this also is just a static shot. The boat isn't actually moving, so the flow isn't really representative of the real operating conditions. In one of my propeller test videos from last summer, I realized that if I can get the RPM of the propeller and the camera's frame rate to line up, you kind of get this effect where it looks like the propeller isn't spinning at all. This is great for observing the flow, and we can use a GoPro which can go underwater, so we don't need the probe lens. I hopped into Onshape and designed this symmetrical hydrofoil that the GoPro fits inside of. By the way, all the 3D models from this video, including the propellers themselves, are available from the Onshape links in the description. Onshape is free for hobbyists, so all you have to do is sign up for an account and you'll have access to everything, including the native design history of all the parts like this one. I 3D printed the GoPro foil on my Prusa XL. It took a few iterations to get the design right, but eventually everything fit together. That whole thing attaches to the side of the boat. Again, it took a few tries to get it right. But now the GoPro can stare directly at the propeller and get awesome shots like this one. Oops. The footage looks good, but it would be better if there was something in the water that would allow us to see the flow better. For that, I designed this crazy looking symmetrical hydrofoil thing that attaches to the front of the drive unit. The goal here is to inject little air bubbles into the water while creating as little turbulence as possible. I 3D printed it on the Form 3 Plus, and the cool thing about this part is that it has little channels in it for the air to flow through. The upper section gets a tube routed through it, and that goes down into the lower foil section. Then the other side of the tube is connected to some little air pumps. The whole assembly is just held on with a Velcro strap, and it looks like this when it's finally installed. In order to get the highest possible shutter speed for the GoPro, I'm using one of the Stratus LED's air modules again. And the bubbler works, so now we can finally start testing propellers. As a quick recap from the first video, what I'm doing here is having the boat run a waypoint mission, and at each waypoint the speed is increased by 0.1 meters per second. Excuse me. It starts at 2 meters per second and then tries to get all the way up to 4 meters per second, but most props can't actually push the boat that fast. Then it turns around and comes home so I can swap props out and do it all over again, 24 times for 24 propellers. I should note that I'm not actually running the efficiency tests with any cameras on board. All the underwater or onboard footage you see is captured separately. So let's start off with our baseline propeller. From looking at the underwater footage, we can see that there are some pretty serious bubble vortices coming off the tips. A lot of people will probably think this is cavitation, but I kinda half disagree. Reason being is that when we don't blow bubbles into the propellers, these vortices are much smaller, if not entirely absent. They do show up sometimes, but it's really hard to tell if a stray bubble hitting the blade is what instigates the visible spiral. A true cavitation pocket occurs when the pressure drops so low that the water turns into vapor. But I think the spirals we're seeing is a mixture of water vapor and air from the bubbles. I think more likely than not, it's a combination of cavitation and ventilation. Ventilation is where air clings to a surface, and in this case, that air would be coming from stray bubbles. Regardless of what's causing the spirals, I think it's safe to say there's a strong tip vortex here. So let's keep that in mind as we look at other propellers. The strength of the tip vortex could be one of the things that has a correlation with efficiency. I ran each propeller multiple times on multiple different days to get a more accurate measurement of the efficiency. And here are the numbers for the baseline propeller. It's currently in first place because it's the only propeller we've tested so far. The integral efficiency is the number we're using to rank each propeller, and a bigger number means more efficient. The intro video talked more about this, but the integral efficiency is basically just the area under the curve when we plot efficiency versus speed. Now let's talk about what this graph actually shows. Here we can see the propeller starts off really efficient. It's making 26 grams of thrust per watt. And by the time the motor gets up to its full throttle power cap of 400 watts, the efficiency is down to 10 grams of thrust per watt. So let's pull our head out of the technical detail bucket and get back to the contest. And auto mode. There's zero wind. It is so nice right now. So I took the baseline propeller and applied a few coats of this nano-ceramic super hydrophobic coating, and then let it dry before running the next test. That's pretty hydrophobic to me. Not quite as hydrophobic as a duck, but it is hard to beat nature. This is an insane new concept that will revolutionize transportation forever. Just kidding, it's pretty average. So the efficiency curves pretty much look identical, and as for the numbers, the super hydrophobic coating actually did slightly worse, but that amount is in the noise. I think it's safe to assume the coating made no difference. Next up is the twin turnip. At higher throttle levels, the tip vortice spirals become visible, even with no bubbles being pumped into the flow. With the bubbles turned on, I was really surprised that there still appears to be a stagnation point behind the hub, even though it tapers off much more gradually than the baseline propeller. I guess the angle back there is still too steep. Here's our efficiency curves. The baseline propeller is on the top for comparison. The average integral efficiency over the course of 3 test runs is 26.9, and that puts it in first place. Aw, the baby ducks hatched. They are adorable little balls of fluff. Wow. Now it's time for the spin doctor. Is this toroidal propeller the miracle invention that all those YouTube videos said it would be? Let's find out. On the underwater view, I don't see any tip vortices. With the bubbles turned on, there is some sort of a spiral coming out of the back, but it doesn't look like it's originating from the tip, which is really interesting. Here's the efficiency curve compared to the baseline propeller. Looks pretty similar. And the average integral efficiency over a few runs is 23.3, which puts it in second place. We'll have to wait until the third video to see if it's any quieter than the others. Holy shit. I left half of a power bar here for like 60 seconds and a bird just swooped in and ate it. Damn it. Next we have the ring glide propeller. I know a lot of people are going to say that I didn't give this propeller a fair chance because it's FDM printed, but in the intro video I tested the difference between an FDM propeller and an identical SLA propeller, and the FDM version was about 15% worse. So if this propeller ends up being even like 30% away from the baseline propeller, I'll reprint it with SLA and test it again. Doesn't even fit. There we go. Oh god, it's so bad. It's already doing 16 amps at only 1.6 meters per second. That's terrible. From the underwater video, I don't see any vortices, which is good, I guess, but this is proof that the vortices aren't everything, because the efficiency was terrible. The integral efficiency is only 0.46, which puts it in dead last by a long shot. But I should mention, this system of measurement kind of falls apart with props that can't go very fast, because a big component of the integral is the max speed. Since this propeller has a max speed that was relatively low, the integral efficiency number we're looking at is going to be disproportionately low. So for cases like this, we should just look at the actual grams of thrust per watt at 2 meters per second, which is about 4.83. This number can't be used in comparison with the integral efficiency, but at least it will allow us to still rank the really bad propellers. Our sixth contestant is bigger, diameter is better. Will the high aspect ratio efficiency promises hold true? Let's find out. I'm just dying over here. It is the nicest day ever. Look how calm it is. It's just dead flat. Wow. If anyone's trying to get rid of their lake house for cheap, let me know. So without bubbles, the prop looks like this. I don't see anything sticking to the blades. No cavitation, no ventilation, no nothing. Seems promising for high efficiency. When we turn on the bubbles is when things start to get crazy. I can see vortices, but they don't originate at the tips. They only start to become visible a few inches behind the propeller. I'm still not entirely convinced this is pure cavitation. I think what's happening is when a bubble hits the core of the vortex, it instantly propagates through it, almost like a crack propagating through breaking glass. But that's not even the crazy part. Look at these wave-shaped bubbles down here. They're incredible. You can see the stream of bubbles getting rolled around the vortex. It's so cool. I think this formation would probably be visible for most props, but this prop just so happens to be the perfect diameter as to where that last line of bubbles just flows in at the right spot. Pretty sweet. So our efficiency curve looks like this, and we have ourselves a new winner. The integral efficiency is 35.3, and the max speed is 3.7 meters per second. Incredible. The wind is coming. Do you see it? Do you see the wind? It's right there. Maybe wind is an overstatement. The breeze is coming. Oh well, at least I've gotten a lot of tests in so far. Next up is nodules and feathers. The real question is whether or not this one will outperform the baseline propeller. In the underwater view, I really don't see any differences from the baseline propeller. Here's the efficiency graph. It also looks very similar to the baseline. And the integral efficiency is 22.11, which is basically the same as the baseline propeller, but slightly lower, putting it in 6th place. Now it's time for the patent-pending Paunovic propeller. Will Nanad's CFD simulation match real life? I'll give this thing a near zero chance of not breaking. It's pretty flimsy. But on the other hand, it does have a super low pitch, so maybe the low pitch will keep it from getting too much force on the blades. Will it break? Will it break? Will it break? It's not breaking. Amazing. In the bubble cam, it looks like the only part of the propeller pushing water backwards is the root of the blades. Out by the tips, you can see flow circulating in from the oncoming water, probably because the pitch of the tip is too low to make any thrust, so it's just making a bunch of drag. It sounds like it's vibrating, so that propeller might have broken. No, didn't break. The efficiency curve is opposite for some reason. I can't quite figure that one out. And notice that it couldn't even get up to the 2 meter per second starting speed. So we'll say this one did 3.5 grams per watt at 1.6 meters per second, which is even worse than the ring glide propeller at a faster 2 meters per second. This puts it in last place. I would really love to see what this blade design is capable of if the pitch were correct, but today is not the day for that. Next up is Fibonacci flippers. I did a quick preliminary test to see if this thing would push the boat at all, and was pleasantly surprised. It's impressive. It actually produced way more thrust than I thought it would, so then I ran it through the waypoint mission. From the underwater view, we can see that the flow kinda seems to converge inwards and it comes out closer to the tip at the back. It looks like there are very few bubbles exiting through the outer diameter. Surely this propeller is not optimized for this motor, so it would be interesting to see just how much efficiency you could get out of a Fibonacci spiral if you spent a lot of time optimizing it. The integral efficiency is 9, and the top speed was 2.9 meters per second, so it beat the ring glide prop by a long shot. I'll give it first place in the novelty category, but it comes in at 7th place overall. Last but hopefully not least, we have the Mars glider. Selective laser sintering. It should be similar in strength to an injection molded propeller. I didn't have high hopes for this one because the pitch and chord length at the tip are both so big that it's bound to have a ton of rotational resistance. This could cause the phase current to max out at a low RPM, which would result in the propeller not getting the full 400 watts.
What you building?
Boat for testing propellers.
Oh, you test the propeller, all the style, different style.
Yeah, very many.
So cool.
Yeah, thank you. So, I ran this propeller for the first time, and it got an integral efficiency of 14, which is pretty bad. So that night I rubbed wax all over it and then melted it with the heat gun. My hope was that this would smooth out the surface finish, and it also turned out to be quite hydrophobic. Then I reran the test. The wax ended up improving the integral efficiency by 0.5, so that's good. From the bubble view, we can see that there are occasional patches of cavitation that stick to the backside of the blades, or it could be ventilation from the incoming bubble stream. Probably a mixture of both. So the Mars glider had an integral efficiency of 14.55, which puts it in 7th place, and its top speed was 3 meters per second. I don't think that low Reynolds number airfoil does much when the rest of the blade design is far from optimal. So that's it for episode 1 of 3. Tune in next time to see if anyone can steal first place from Bigger Diameter is Better. And don't forget to subscribe and click the notification bell to never miss an episode. Big thanks to everyone who submitted a propeller, and also big thanks to Formlabs for supplying all the resin for these propellers, PCBWay for supplying the prizes, Mitch for helping me with the data collection system, Holbrook Aerospace for the baseline propeller template, and Sebastian for helping me with the Mavlink data stuff. That's all for this video. Thanks for watching. Bye.